minutes, but yes.
Okay, go for it.
Do you have a presentation you guys can share with us?
Very new to us. For a few months.
Okay, you were jumping out a little bit. Do you have a presentation? I didn't hear.
We do not.
Okay, so all right, so then why don't you introduce? Yeah, so have the students introduce themselves.
Illustrations, though, that we could discuss.
Yes. Okay. So why don't
you guys go ahead, introduce yourselves. I'm going to go grab the drawings.
Yeah.
Okay.
Introduce yourself and tell us what your role is on the project.
Hello, my name is Thomas Barnes. Playing around with our trying to figure out.
There's a lot of static.
A couple of designs of that.
Your connectivity is problematic. We're not hearing and understanding anything you're saying.
Yeah. There's some static somehow going on.
Yeah, try it again, and then Dave and Flo, let's us mute and see if that helps too.
Can you hear me?
Better. Keep talking.
All right. My name is Thomas Barnes. I've been working on the chess set that we've been trying to figure out how we can properly make chess pieces stick to the board in space with zero gravity. I've been playing around with a couple of different designs and trying to think of how I can do that in the most simplistic way possible.
All right, and then next, let's the next person talk. Introduce yourselves and what have you done in the project?
I didn't plug it in. I gotta go.
Yep, you can go.
I can't hear.
Oh, you guys lost us?
Is it?
Can you hear me? No?
Oh, yeah, we can hear you now.
Okay, so
Sorry.
you go ahead and tell me your name and what you're doing on the project.
All right, I'm Alex Sheets, and I'm working on the trash ejector. Just helping Tommy out for the chessboard.
Okay. Tell us about the chess project so that we can get started here.
Yeah, what are you doing on the chess project to help him? Oh, yeah.
Okay, so for the most part, we have kind of just been trying to think of like different ways that we can get the chess pieces to stick to the board. So originally I was thinking that we could do something like have them click into place somehow. So if you've ever seen like
everyone can hear us.
with like clothing or like buttoning, like you can like stick like a shirt together, or like your pants or something like that, and then
Like the buttons. Yes, how the buttons go in and out.
Yes. So I was thinking we could possibly try and do something like that on the chessboard, because that would be pretty simple.
Okay, well then that's a good way to start. You want to find something that already exists, like you had there's like snaps, there's like buttons. Find something that already exists. That's a good start. Okay.
This conversation, the big general.
All right. And what about the other students? What have they been doing on the projects?
Specifically, they've been providing a lot more of kind of a sounding board. We don't have necessarily teams per se. It's predominantly the group, and we split up to discuss ones that interest us. Thomas is the one who's the most intrigued about the chess. So that one has really been his bread and butter. Everyone has listened and provided their input, especially when it came to discussing the materials. However, a lot of our questions do come from, honestly, most of our conversations regarding the chess one has come from even right behind us, the materials that can be used. when we first reached out, we heard about like magnets are obviously like it's a no-go. There's not going to be magnets thrown out in space. That's the point. But figuring out, like looking at this, when it says like the polymers, in what form will they be in? Will they be in bags that can be cut up? Are they going to be more solid pieces?
I see.
We're trying to figure out a material list.
Okay, so I would say, yeah, and you bring up a good point. So that's where the research comes in. So one of the things you want to do initially is research. So with chess from trash, you want to look at what are the different types of trash, what are the different types of plastic that's on station, what is it that you can use and utilize. And I believe there's like 2 different parts to this. You can decide to take the plastic and use that as a method of extruding, or 3D print the chess. So that's something else you want to decide, because I think there's 2 paths depending on what you're doing. And from your research, you can find, what are the different things that's there. You can also research how has trash been used for other items. So the researching is good, kind of like you're researching how to stick together. And then that's where I mentioned, look at the constraints. How are you going to make the board? Different things like that. Glenn, you have any other initial ideas? Because they're stuck on the materials, and I think there's other things they can also work on.
Okay, well, tell me what you guys have done. Are you just doing research? Have you built or made anything yet?
We have not yet, we don't have like a prototype yet or anything like that. We've just been kind of like sketching out ideas on paper and, kind of just.
Okay.
Like
and so what kind of theme do you want to do with your chessboard?
I'm sorry, could you repeat that?
What kind of theme do you want to do with your chessboard?
Theme?
Do you want it to be? Yeah.
So what kind of pieces are you planning to make? Are you just doing standard chess pieces? Do you have some other thoughts on how you want to do that?
Yeah, we were mainly just thinking about doing like standard chess pieces.
Okay. Well, and so part of the deal is that these people are going to be on the moon, right? And so they're looking back. They don't want to be space people. They don't want to be just playing with like chess pieces that are designed after astronauts, because they already know they're astronauts. But this is a chance for you to do something very creative. So just standard chess pieces, we can get that. We've already got that. Can you guys come up with something new for that? Does that make sense?
Yes. Okay, I understand.
So, for example, consider you could do sea animals versus animals of the Serengeti, right? Or you could do my family versus your family, right? That's really specific, right?
Or you can do dinosaurs versus something else.
Dinosaurs. There you go. See,
that's where you get your creativity. Yes.
Open this up to being something new. Does that make sense?
Yes.
So there has been. I don't want to poke in. I understand. My crew can understand. I'm honestly, I'm a little nervous. It's kind of cool that it's cool and terrifying to be talking to NASA and hearing and ideas. And I'm looking forward, obviously, by the next time the like, oh my God, this is happening, is kind of wearing off by that point. So my students here.
Oh, hold that up so we can see.
Oh, I will. They tend to do 3D design and 3D printing. So one of the things that some of my students here have done is made a non-Euclidean chess, and it's wormhole chess.
I'm okay with that. That's very interesting. Tell me about it.
So this was just like a goof idea that we weren't originally going to move forward. Tommy's been spending so much time focusing on the mechanism to get them to attach that ultimately the creative aspect is taking a backseat because they're focusing on the actual build. Doesn't matter how good if it looks if it doesn't actually work. But the whole idea of the non-Euclidean one would be this plate would be replicated and attached to the back, and you would have the pieces go through the quote-unquote wormhole onto the other side. So that way you could either have 4 people playing at the same time, 2 people battling on a regular chess field that is with a hole, or have one on the front here and one on the back, say down here, and you must battle. So there's different variants that you'd be able to do. It's just a matter of the mechanism. And that is where everybody has been really focusing on here. And even for the other projects, the mechanisms have been honestly our biggest discussion, like argon versus helium. And yeah,
Okay.
we get caught up on some of the details.
And that's okay. Our biggest deal is that we are trying to get an idea from your head to an idea in your hands. And so I'm trying to look for what kind of process are you having for how you're going to get it into your hands. And I like the idea that you're working on some kind of a button method for holding the pieces. What kind of trash do you want to develop, or do you want to use to get to your board or pieces or whatever?
Yeah, so we've been looking at different materials and types of things, but we don't really fully know what kind of materials might be like present, I guess.
So actually, you need to keep watching Glenn's his site. It's hunchdesign.com. And on slide 4, this is such a common question. On slide 4, Glenn has added in highlighted green a chart that tells you what is some of the trash on the space station. So we're using the space station now, the ISS, because we don't have one on the moon or Mars, right? But you'll see a whole list. He has a chart of things that you could use.
And that's important to go back, because I mean, that's where you start. He has textiles, polymers, metallics. There's a listing there. And then that's what you use to describe how you would make that. I like that design, but I think, like Glenn says, figure out how would you make that using trash.
You said slide 4?
Yep.
I believe we have looked
Table
at
4.
that.
So let's mentions like the PE and PP polymer, etc.
Yes.
We were curious, I guess, kind of in what state, like how would we, when we're thinking, say we want to use nitrile, would it be from gloves? Would it be in sheets? Approximately, like the quantity and dimensions of material.
That's
So,
where
and
the research. That's where the research comes in. So something
But
like
you're-
nitro. Yeah.
Gloves. Start with
Gloves.
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 Yeah.
Makes sense, right? So you're not going to have sheets of it. You're going to have gloves of it.
Right.
So we're not going to be sending generalized materials. We're going to be sending specific
Material.
equipment, right?
A lot of come into the research aspect.
Right.
Makes
This
sense.
is all
Okay.
about recycling what we use for other purposes up there. We're not,
Yes.
that's the whole object of this.
Yeah. So if you think of the nitrile gloves, it probably won't be a complete glove. It may be a glove that's torn. And that's why they throw it away. So then that's where you want to play around with that. Hey, can I take a glove and make a piece out of it? You know, things like that.
Now, the other part of this is that a lot of the materials that we send to space are not, they're not very recyclable. Okay. And the reason for that is because they're not very flammable. Right. And so as much as I would like to say, only use things that we send to space, they're not very recyclable. So some of the thing that I need you to do is find some materials that are recyclable, research them so that you know what the problem is of why we may not be sending them. It's probably because they're a little bit flammable. But if NASA wants us to recycle materials on the moon, then we have to be ready to send materials that we can recycle to the moon. So show us what kind of things you can recycle and what you can turn it into. Does that make sense?
I would also suggest that instead of just using the word recycle, think repurpose. Okay? If we're recycling a plastic, that involves a process of, the recyclable types of plastics are usually ground up, reheated. You can take a milk jug and recycle that type of thing. But you could also take a milk jug, and cut it up with an X-Acto knife and make things out of pieces of that jug. Does that make sense? So I don't want you to restrict yourself to thinking that you have to use the same, criteria that a recycling center on Earth does. You can simply repurpose. I would encourage you guys, creativity is often, it comes from having things in front of you that you can pick up and hold and say, what can I do with this? How can I manipulate something like, again, a plastic milk jug or a water bottle or, an aluminum can? There are, my grandkids love these little fruit juice pouches, right? Now, we're not going to be sending fruit juice pouches, but we will be sending probably the same type of thermo-prepared meal packets that we send to the International Space Station. The material wouldn't be the same, but again, if you had one of those, how could you cut it up and maybe weave something from it, or bend it, shape it, etc. This is all about trying to think out of the box and being as creative as you can. I would also mention that, as Nancy said, we created this project with two different directions. Additive manufacturing, we're going to take extruded plastic and print something, or just take material and, again, repurpose it. You can also do a hybrid, right? You could make some of this out of 3D printed and then use just pieces of trash in other forms. So, one of the things that I would encourage you to do is just go find a recycle bin there in the school and start going through it and thinking, what can I do with this stuff? How can I turn this into a pond? How could I turn this into a chessboard, etc.? Okay? Because it's all about creativity, guys. And you're as creative as anybody else. I bet if you start playing around, you'll come up with some interesting ideas.
You bet. And I actually have some samples. This is a drink, this orange drink for the astronauts. And believe it or not, it's just made from Capri. You have Capri Suns, those little drinks that you can buy at the supermarket. It's the same material. You can start drinking Capri Suns and use the material. That's recycled material. This is the plastic that's on the food. Cut this up. After the astronauts have a delicious mango salad, you could use even the caps on it. They could recycle. And also, there's a lot of material. There's a lot of projects that use material up there on the space station.
Sure. What do you do with an old shirt or a pair of pants or something? You can rip it up and cut it up and do all sorts of different things with it, right?
So, what kind of questions do you guys have?
So the whole idea is that we're trying to use materials that we have here to replicate ones that are given on the space station?
Something like that. The purpose is we're trying to figure out how we can reuse materials on the moon so that we're not throwing everything away. So we don't have to send all of our stuff so that we don't have to spend $1.2 million per kilogram to send something to space, that we can use some of the things that are already there.
So like not taking up any more space, so utilizing the things that you already have, right?
That's right. So you're on the moon, you're going to make something out of what's there.
Yeah.
Something out of nothing.
That is not usable anymore. So we wouldn't cut a good T-shirt up, but we would a dirty one.
Cool.
Does that help?
Does that help, guys?
Okay.
Yes,
Thank you.
absolutely.
I do have a bit of an odd question. So some of the specialty, like I'm really hands-on personally. I run the makerspace, so like when I think about foam, I have like 30 different types of foam back there. So I'm looking at Zotec F30, and I'm curious: are there places in particular that you recommend potentially buying some of this material so we can at least see it? Like, I'm assuming it's denser than other foams that I have, and such
It's
and
kinda
so
like-
forth. So that way
It's
we can
kinda
at least.
like, the foam on your shoe.
Oh, okay, yeah, wow, that's definitely denser than the stuff I was thinking of. Yeah, all right, okay.
Okay, but do they have to use exactly Zotec to demonstrate with? Definitely not.
Yeah.
I mean,
Yeah,
right now, I just want you to show us what kind of ideas you have for making some of this, some of your ideas.
absolutely, absolutely. That makes sense.
What you should do is pick a material that's similar, let's say, to the foam they want, but you don't have to have the same material, but you should know when you exhibit your stuff and you're going to go to a Rochester Institute of Technology, and that's February 6th, you should be able to tell a reviewer, well, NASA should use this type of foam, but this is what we're using. It's similar and it's not expensive, and we have it handy.
Of course,
Don't
of course.
go
that's what it
buying
sounds-
expensive material, in other words.
Oh, come on. Don't ruin the fun. I want to play with NASA foam.
NASA foam, right?
Where are you guys located? Are you in New Jersey?
New York. They're in New
Oh,
York.
Okay, and
They're
that sounds
100 miles from Rochester. Because I wanted to go visit you, but my person who was driving with me, I said, "Oh, you want to go 100 miles today?" He said, "No," because I was at Rochester.
Come on.
That was
We'll
so we
meet you
never
next
got
time.
to.
It'll be fun.
Yeah, well, you come to Rochester next time.
okay. All right. Do you guys have any more questions or comments?
Do you? It's okay if you don't. We still have two more. In regards to the chess one, I don't believe so. If anything, although a lot of the feedback we've gotten here will help us prepare for the next one, especially since I know that these other two, after this, we're going to start testing the strength of various filaments that we got for a later sample box, for goodness sake. So yes, we have, hearing this was very helpful for us to understand how to best present and converse.
Okay.
Yes.
So did you guys want to talk another one?
Yes.
If we still have some time, yeah, please, by all means. I will tilt this a little closer to these two gentlemen. What? Oh, no, good point. Good point. Actually, I will do like this because Felix, you're right. Felix also loves. So, yeah, everyone will all get nice and close and it'll be really wonderful. Oh, the box. All right, so this is the PLA version of the box.
It's fine. It's fine.
Yeah, I just got the glue stick on there for the PC.
The problem with the original lunar sample box was that it was leaking air into it and contaminating the samples, I believe.
Carbon fiber PC.
So our idea was that why bother sealing it if the box can be porous? And then let's say you wrap the sample in a layer of silicon or resin, and underneath that is like another layer of like plastic to protect it from the resin, because
So do you mean like put it into a liquid or whatever so that it's all coated, or what do you mean?
yeah, so you put the sample into like a plastic bag, then you put the bag into uncured resin. The resin cures, and it's completely airtight, so that it can't get contaminated. And then the box just acts as storage or to protect from blunt force.
Okay. I'm not opposed to that. I mean, first of all, they have very limited materials that they want to touch the rocks. And so the first baggie would be like a Teflon material. Okay. And that's okay. Now, the next idea, though, is by putting it into the into the silicon, do I have to worry about that getting on my spacesuit?
Not sure.
That's something to think of. I'm glad you brought that
Okay.
up.
Yeah.
And so
Yeah.
I'm not opposed to that idea. Just remember that you're going to, so if you put it in the Ziploc bag, you put it into the container, I want to make sure it doesn't get on a spacesuit. But the other thing is, does it cure the same way in a cold vacuum as it does here on Earth?
So we were thinking of using UV resin so that the natural UV from the sun cures it.
That's actually really interesting. I hadn't thought of that. That could be good. Now, one difficulty there is if I pick up that rock in a cold air, an area that has never had sunlight. That means to get to the sunlight where I'm going to get the UV, I would have to carry it out first. I don't know if that's a problem, but it could be an issue. Does that make sense?
Yeah, we'll keep that in mind.
Okay. UV curing that's also a really smart idea. What do you want? Could you put your silicon material so that it maybe when you close the box is when it injects it in?
Yes, possibly.
Because if it's so the material essentially that we were testing out with or starting to test out with, it's the hardener and the actual material, and they do come in two separate vials because they don't actually work until they're mixed together.
Right.
The only thing we would need to work out, and that's a thing we need to discuss, would be mixing it so that way it actually hardens proper. Because if it doesn't harden properly, well, it doesn't work. So theoretically, inject the material, place the object in there, and then it cures around. So that way we can mix it without having to worry about beating the rock up a whole bunch.
Right. Okay. Now, the other thing that's important, so you can imagine that sometimes you're going to pick up a rock, and we said baseball size. Sometimes they might pick up just dirt, put it in the bag, and then close that up. Now, and part of what we're looking for is when I scoop that up and put it in, it might have some ice in it, right? And this ice at the time is going to be something like about negative 400 degrees. Okay, that's pretty darn cold. And so when we put it into the box, the biggest reason why we want to make sure that we're not contaminating it is because we want to find out how much water ice might be in there. Does that make sense? And so an insulation is also something that could be valuable. I mean, as soon as I close that lid and start walking around with it, it goes from being negative 400 degrees Fahrenheit. Now I walk into the sun, and one side of it is in the shade where it's like negative 250, but on the sunny side of it, now it's positive 250. And so having some kind of insulation to minimize how much we're changing that temperature would be great. But here's the problem. Now I walk it inside of my spacecraft. I let the air pressure in on it. So now it's trying to squish it. But it also gets up to 71 degrees or so Fahrenheit in there. Now, there's no way for us to be able to keep all of this stuff all at the same temperature all the way from the time that we pick it up to the time that we bring it back to Earth. But minimizing how quickly it changes from one temperature to the next would be helpful. Does that make sense?
Mm-hmm.
If this sounds like an impossible task, you're not far off. It's really hard. So we are looking for the best possible solution to be able to handle all of these difficulties. Does that make sense?
Yep.
I would also recommend having a conversation with your chemistry teacher and your physics teacher. The idea of resins, etc. These are all fluids, right? And you're in a vacuum. Boiling points, etc., change dramatically. I'm not convinced of the feasibility of trying to use in an environment where you're in a vacuum. You've got a space, somebody in a pressurized spacesuit trying to work with those types of materials. First of all, if you open the bag up, I think this stuff is just going to it's just going to boil off in a heartbeat. It's not going to stay very well contained. But I could be wrong. I think that you should have a feasibility discussion with your chemistry teacher and your physics teacher about, is this a realistic or a practical approach to take?
That's something you can test, though, right? I mean, if you guys took some of this epoxy material or silicon caulking or whatever, put it into the bell jar. Your physics teacher or chemistry teacher, they have a bell jar. You guys could suck it down to a vacuum, and it would give you an idea of how that would work.
Yeah, there you go.
And it might generate. So some epoxy materials will generate their own bubbles and it'll foam up. And if you do that inside, that might actually save you from how much material you would need as well, because it's going to foam up even more in a vacuum chamber. So that could be valuable. But will it actually harden up correctly the same way? I don't know. I know that NASA did some testing on that when they were looking at how to repair tiles on the space shuttle. So, anyways, you guys have some interesting ideas.
Yeah.
Don't be afraid to explore and test them. Okay.
Thank you.
So one more thing. As you mentioned with the temperatures and how it's going to be like negative 250 up there, is there a way for us to mimic those temperatures like down here? Like, yes, negative 50, so we can test like specifically how certain filaments would handle in those temperatures.
And the shock from negative 250 to positive 250.
Yeah.
And it's Fahrenheit, guys. It's not Celsius.
That's Fahrenheit.
Fahrenheit.
And I round that off. If you look it up, you'll find that they are a little bit different temperatures. But liquid nitrogen, if your teacher has access to be able to use liquid nitrogen, you could check some of those things as well. And that's how NASA does a lot of its testing. They want to check how a material behaves at those temperatures. So they'll dip it into some liquid nitrogen and then tap on it and see what kind of tests they need to do with it.
Okay, nitrogen it is. Perfect. Sorry, that's been a big one. We've been contacting Cornell trying to take advantage of some of their labs, but ultimately,
that sounds great.
They haven't been as successful as we would have all liked. And trying to access the positive 250 is easy. The negative 250 is a little bit trickier in our school. Our freezers go down to negative 20.
So what's liquid or what's dry ice at? I forget. Is that
about
like
minus 88?
Oh, is it?
Yeah.
Okay.
Yeah.
That's approaching, and it would give you some ideas, right?
It will give you better data than you can in a freezer.
That's right.
It's not the best, but yeah.
Well, for example, if you use a rubber seal, right, that has some pretty specific range of where it's still rubbery. Whereas if you check on a Viton gasket material, I believe it has a little bit more wider range of temperature capability. So Viton is one of the sealants that we use on the spacecraft right now, and that would be a recommendation. Look and see if you can get a piece or two of that. It's fairly common, so it's not unheard of to be able to find it at a hardware store or something like that.
Okay.
But the The real challenge is to keep the air in your container and keep the air from the habitat on the moon out of the container.
Well, so consider, let's say you take a box. Okay, pretend you pick up an ammo box, right? Like for ammunition kind of stuff. If I was to take that to the bottom of a pool, that would be a similar kind of pressure range. How much water would try to get into that box if I took it to the bottom of a 10-foot swimming pool?
The answer's all of it.
All right.
And we have access to a pool in town.
So our
That's right,
original
12.
idea kind of is different than that. I don't know if it's a good idea or not, but we believe that the resin or silicone would be the barrier to protect from the atmosphere or pressure. And then the box would have a porous-like lid so that there's no collapsing in on itself.
Mm-hmm.
A porous lid. Okay. And so part of what you're thinking is you encapsulate them into some epoxy material, and the box is just there to give it a specific form and stackability or something like that when I get it into the spacecraft. Is that what you're thinking?
Yeah.
That's not bad thinking. Exactly how that's going to work out yet or not, I don't know. But I continue to explore that. That's not bad thinking. Now, if I don't have any containment from the box itself, that means that your epoxy material is taking that air pressure against it, right?
Mm-hmm.
And so it would be the same kind of issue. But if there's no voids there, bringing it into the pressurized spacecraft is probably not going to do very much to it. So it's something to consider.
Mm-hmm.
All right.
Makes perfect sense.
What kind of shape are you thinking about for that exterior box container?
So I've been pretty much designing the container itself. So how I measured it is I essentially took the dimensions of a baseball and multiplied that by 2 for the length. So it's slightly bigger than a baseball, and slightly longer than a baseball.
That one was cut in half, by the way.
Yeah, this design right here is cut in half, as you can see. But
okay.
It can fit 2 baseballs in it, and the lid on it is a little bit taller than that, so it should also be able to easily support a baseball-sized rock or dust, as you said.
Sure. Yeah. I'm okay with that. And so one of the things that I didn't put as a requirement, but something you should be thinking about is just, so you get this box back into the spacecraft, you're going to take off. What are we going to do to hold it down or keep it from floating around once we're in space, right? Do we stack them? Are they cylindrical and you kind of put them in some kind of a square case? Is there a space like a little closet or something where they kind of stack up or something like that? So it's not a requirement, but it's something that makes sense that we want to be thinking about as we develop this box. Okay?
Yeah, so kind of like a modular system. So
and so, I mean, if you had something with your box so that it was stackable with the next one, or maybe it has some kind of ridges or something like that, so I can slide it into place on the spacecraft, or there's a lot of different ways that we can store these boxes. And if you have an idea of how you think they should be stowed, we'd like to hear it. Okay.
All right.
Do you have like a rough estimate of how many we're looking to store?
It's a great question. And tell you the truth, I aimed at 2 baseballs just because I wanted to give you something that would be, I didn't want it to be some kind of expensive project. I wanted it to be fairly small. So you can imagine that NASA might come back and say, we don't want just 2 baseballs. We want each box to hold, 5 baseballs. I don't care. I don't know what that's going to be. But right now, for you to let's pretend that NASA wants to bring back a total of 30 baseballs. So that means we might have 15 of these boxes. Does that help out a little bit?
Yeah.
And this is just making some kind of an easy estimate for what they might want to bring. Okay.
All right.
Yeah.
Terrific.
Keep reaching out to was it Cornell? Sometimes if you copy your NASA hunch, like Nancy's your mentor, and she has a nasa.gov email, you might get a better response. Tell them that you are working for NASA. Do you still have a trash ejector? Any of you guys doing the trash ejector?
That one's a work in progress. Our debate was predominantly on gas would operate the best, and oh no. Yeah. All right, go ahead. Talk about argon.
All right, so I was mostly looking at using like a pneumatic type of thing to use for a trash ejector. So you would push a button and it would eject the trash out of the box or whatever, the can that you have it in. So at first I was thinking possibly about using like maybe non-reactive gas like argon or helium. I think we ultimately decided that helium would work best in a space environment.
What do you want to do with the helium?
I want to make a system, a pneumatic system that so when you press, so like.
The gas is for
This one's a very, very big work in progress, i.e., still discussing.
Right. Yeah.
Very, very early stages. Most of our work has been on the lunar storage container. I will be dead honest. A lot of thought has gone into this.
Well, and I don't know how many teams you've got working. I mean, you've got what, 4 or 5 people working all of these, or what?
Yeah, I think we pretty much have 7 consistent people, and they're working all of them. And we removed a couple of them because they sounded cool, but we don't have the methodology, or this is still brand new to us.
Well, how about that? I would suggest you choose 2, and kind of stay on those 2. Otherwise, you're diverting your time to too many things, and it makes it hard for you to complete any one of them. But let me put it this way. So I'm not opposed to pneumatic systems in space as long as I'm not throwing away the air that you're using. And so, for example, whether you use helium or argon or whether you use just the air from the spacecraft, I'm okay with that. All of them would work just fine in space. So imagine if I have air coming in this side and then I'm pushing out on the soup can with this side. That works perfectly fine. And then somehow you pull it back in so that you can put in another can and eject another one. Does that make sense? Is that kind of what you're thinking about?
Yes, that's exactly the idea.
Okay. And there's no reason why you can't use any of those gases. Why do you think you need helium or argon?
I mean, I guess it was just the idea of like what we might want to use, like, because if you're thinking about like something that's going to be outside of the spacecraft and exposed to elements of space with the pressure and the temperature. I was thinking that maybe helium best or well, a gas in general instead of using a hydraulic system, that'd be a lot more harder to do based on pressure and temperature, mostly temperature.
Okay.
With a gas like argon or helium, especially with pressure, it would be easier to just use that, I guess.
Well, for the most part, your gases are going to they're going to be pretty much the same kind of compressibility. I mean, obviously, if you let oxygen or carbon dioxide or these, as you cool them down a lot, yes, you would get some of them to precipitate out as liquids or solids eventually. But for the kind of things that we're doing, you're not going to be letting them cool down that much, right? So, for example, you would kick out one can and then you'd pull it back in, and probably a couple weeks later, or a couple days later, you'd do it again. But for the most part, you're talking about exposure for a couple of minutes. Does that make sense?
Yes.
So I think that for the time exposure and the cooling that we would get, it would be fairly small, and we wouldn't have to use specialized gases. I think you could just use regular atmospheric, which is going to be a combination of oxygen, nitrogen, some carbon dioxide, and then some other trace gases. Is that okay?
Smart. That actually saves.
Yeah, that saves a lot of time and money, actually, probably.
You would spend 3 weeks argon for nothing. Good. I can't wait to tell Felix.
Okay. Any other thoughts or questions about it?
But that's exactly why we have the reviews, to make sure you're on the right track. So
That's right.
that's important.
Okay. Any other questions?
Can we buy one of the NASA trash bags? We saw it on the Hunch design. We were curious out of sheer curiosity. The NASA trash bag.
Glenn, is this like the trash bag that they're going to be?
Yeah,
and I bought this at REI, I think.
That's right. And that's where NASA buys them too. Is that a 9-liter?
Are you kidding? I'm going to REI this weekend. Done. Sorry, I'm hearing you out.
I don't know how big. What size did you?
The space program uses a 9-liter Sea to Summit trash bag.
Yep. This says it's 7 inches diameter, 15 inches long, I guess, and it's REI, made in China.
Okay. Oh, there.
My friend is one of those.
That is ridiculous. Well, we were looking at the design site. It said I thought it's a shop for items, and it would show trash bag.
We missed a lot of what you're saying, but yeah,
it's fixed. So oh wow, imagine buying.
Yeah. No, whenever you're not sure, just ask a question. Send us a question, and we'll answer you right away. And actually, Nancy's your mentor, but you could send it to any of us, but copy Nancy.
It's crazy.
Okay.
Of course.
All right. Any other thoughts?
That's cool. She's gonna be best friend. At the moment, I'm excited to
You're breaking up now.
The progress we've made on these upcoming projects a bit more. you guys
Yeah.
say. You're closer.
Yeah, you have to be real close to the computer. Otherwise, we get static.
Okay.
Everyone gets closer. Yeah. Go ahead.
All right, guys. I got to jump off for another meeting too. So keep up the
Thank
good
you,
work.
Dave.
You bet.
Thank you.
We'll talk to y'all soon. Bye-bye now.
Okay.
All right.
Bye-bye.
Bye.
All right.
I think
Sorry,
that's
You're closer.
you're breaking up.
I think they're done.
Okay, bye.
Yeah.
Bye-bye. Thank you so much, Glenn. You have a great weekend there.
Okay.
All right, bye-bye.